Hi, the topic of this video is an impulse train or a stream of impulses. In my previous video, I talked about the unit impulse function, unit impulse function, which is also called as the delta function. Delta function. And if you recall from my previous video, the delta function finds immense applications and utility in the analysis and understanding of signals and systems, and therefore it is an important concept to be understood. As we see in this figure here, the red line is an impulse function which is located at time t equal to 0, and this black one is also an impulse function but shifted and located at time t equal to 1. Basically, an impulse function is a function that exists only at a specific time, and for all other time values the amplitude of the function is 0. So the red impulse is existing at time t equal to 0, and this black one is existing at time t equal to 1. Now, in many cases, we may come across a situation where a signal comprises or it is composed of many such impulses. It's a combination or sum of many such delta functions. So, for example, if we have a signal which is a collection of these two impulse functions, and if we call that as some signal, say y of t, then it is simply a summation of these two impulse functions, which we can write as delta of t plus delta of t minus 1. Now notice we are taking the independent axis as the time axis. So the x-axis here is denoted by time. It could be any other variable as well. So the independent variable here, we are considering it to be time. And later on we will see that it can also be frequency. So to have a signal which is composed of many such impulses, it's basically a summation of those impulse functions. Now in many cases, we can also have situations where we have a stream of impulse functions which are shifted versions of the impulse function. So what we see here in this figure is that we have an impulse function at time t equal to 0, and it has an amplitude 1, and there's also an impulse function at time t equal to 1 which has an amplitude of 1. So it's a collection of unit impulse functions located at time t equal to 0, 1, 2, 3, 4, and so on and so forth, and similarly at time t equal to minus 1, minus 2, minus 3, minus 4, and so on and so forth. So the signal which is comprised of these impulses is basically a summation of all these impulses together. And notice again that the independent axis is taken to be the time axis, and the time separation between any two impulses is taken to be as one time unit, or suppose we say in seconds, it's 1 second. Now the time separation can also be any other value, but if it is 1 second, then we represent each of these impulses as delta of t for the impulse at t equal to 0, delta of t minus 1 for the impulse at t equal to 1, delta of t minus 2 for the impulse at t equals to 2, and delta of t minus 3 for the impulse at t equal to 3, and so on and so forth. And if you recall again from my previous video, wherever the sign here is negative, it means the signal is, or the impulse is shifted to the right, and wherever the sign is plus, it indicates that the shift of the impulse is towards the left. So a negative sign indicates a right shift, and a positive sign indicates a left shift. Alright, how do we represent this as a signal together? What would be the mathematical notation to represent a signal which is comprised of these impulses. It is basically a summation of all these impulses together. Now, instead of having the time separation between these impulses to be one time unit or 1 second, it could be any arbitrary value which we can call as uh, ts. The time separation is ts, so it is a separation of 1 ts unit between two impulses. So the first impulse, the first shifted version occurs at time ts, and the second one is at time 2ts and 3ts. Similarly, on the left shifted versions, we have at time minus ts, minus 2ts, and at minus 3ts, and so on and so forth. Again, a signal which is comprised of these impulses would simply be a summation of those impulse functions. So what we're trying to do here is, when we have such a signal, or we want to see what would be the mathematical notation to represent such a signal. Right. So how do we represent such a signal? As it is just a summation of those impulses, and if I call such a signal as some signal, say we call it simply as y of t, it is basically equal to this, the first impulse delta of t, so we'll have it as delta of t, and I will write the impulses which are on the right side first, and then I'll write the impulses which are towards the left, and then we'll put them together. So it's delta of t plus delta of t minus t plus delta of t, so that's minus 2ts, plus delta of t minus 3ts, plus delta of t minus 4ts, plus so on and so forth. And then if we write of the impulses which are on the negative side, we can write the plus delta of t plus ts, plus delta of t plus 2ts, plus delta of t plus 3ts, plus delta of t plus 4ts, plus so on and so forth. So to represent this in compact notation, we can simply write this signal y of t as, we can use the summation notation, summation delta of so it's summation delta of t minus n ts, where n goes from minus infinity to infinity. So whenever we have negative numbers for n, it will become minus of minus the value of n, which will become t plus some ts, and whenever it's positive number for n, it will be t minus some value of n times ts. So basically we can have this notation for y of t as y of t equal to a summation of impulse functions which are shifted by amounts which are integer multiples of the time shift ts. So we have an impulse at t equal to 0, at t equal to ts, at t equal to 2ts, at t equal to 3ts, and so on. So it is just a collection or summation of those impulse functions. Now when this ts is equal to 1, as we had in the first graph, so when ts is equal to 1 second or 1 time unit, so ts simply becomes 1, so we can write our y of t as a summation of delta of t minus n, simply, where because ts is equal to 1, so where n will become, or it will range from minus infinity to infinity. Alright, Now, so far we have seen that these impulses are located on the time axis, but we can also have situations where the independent axis is some other variable other than time, and a common variable that we will come across in signals and systems, signal processing and communication systems is the frequency variable. So we can have, instead of time as the independent variable, we can have frequency as the independent variable, in which case we will simply denote each of these impulses as delta of f, and this one will be delta of f minus 1 fs, delta of f minus 2 fs, that should be fs, and so on and so forth. Similarly, on the left side it will be delta of f plus fs, and the second one will be delta of f plus 2 fs, and so on and so forth. In this case, we will have a function which is a function of frequency rather than a function of time. So we can simply call such a function, say we'll call this as let's say x of f, and just to keep our notation clear, we'll call it as say capital X of f, which is nothing but the summation of all these impulses, delta of f plus delta of f minus fs plus delta of f minus 2 fs plus delta of f minus 3 fs plus delta of f minus 4 fs, and so on and so forth. And similarly, the left shifted versions would be delta of f plus fs plus delta of f plus 2 fs and delta of f plus 3 fs, and so on and so forth. Or in concise notation, we can simply put that as x of f is equal to summation of delta of f minus n fs, where n ranges from minus infinity to infinity. Right? So what we have seen today is the concept of an impulse train, also called as a stream of impulses, which is basically a collection of impulse functions which are separated, which are equidistant from each other, or two consecutive impulses are separated by the same amount, and a collection of such impulses, which could be either in the time domain or in the frequency domain, depending on which is the independent axis. These are called as an impulse train or a stream of impulses, and these find useful applications in the analysis and design of signals and systems, and in the understanding of a lot of concepts related to communication systems and signal processing. Okay, thank you.